Hey guys, it's Mr. Lum, and we're going to be doing some KEQ stuff, and we're going to be looking at something else. Sorry I'm away today, not feeling the best, so anyways, let's jump into it. Anyways, here's a question right here. This is in the handout that you should have, that 2.3 handout, and if not, the sub should have a copy of this handout. Anyways, here's the question right here. It says given KEQ for the reaction PCl5 turning into PCl3 plus Cl2. It's gas, 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 so we don't have to worry about any solids. So everything is going to be in our KEQ expression. It gives us the KEQ. It says the KEQ for this thing is, and let's write it up here, is KEQ equals 0.042. That's our KEQ. So I'm going to kind of write this whole equation out again, just for fun. PCl5, and I should be writing the states. I'm just a little bit lazy, so I'm not writing the states right now. So Cl2, and I should be writing gas, gas, and gas right there, but that's the way it goes. Anyways, and it says in this 1 liter flask, that 1 liter flask, 2.5 moles of PCl5 is dumped in there. So this is going to be 2.5 moles. Since it's a 1 liter flask, it's going to be 2.5 molarity. The PCl3, where's that stuff? The PCl3 has 0.6 moles dumped into it. So in a 1 liter flask, that's going to be 0.6 molar. 0.6 divided by 1 is just 0.6. And for chlorine gas, it's going to be 0.6 as well. Okay, so all three things are dumped in there. We're given a KEQ, and what we want to know is this thing going to shift left or shift right or not shift at all? So we have concentrations of the reactants. We also have concentrations of the products. Okay, so I'm going to make a KEQ expression right now. So my KEQ expression looks like this. KEQ equals the concentration of PCl3 times the concentration of Cl2 over the concentration of PCl5. Since we have a 1:1:1 ratio, there's no exponents in this equation at all. Anyways, so this is our KEQ expression. Now, we know that the KEQ at this given temperature is 0.042. Okay. We also know that 0.042 means that it's favoring the, well, since it's less than 1, it's going to be favoring the reactants. Now, is this at equilibrium? That's what the question is asking. Are these concentrations telling us that this is at equilibrium? So we are going to test to see if it's at equilibrium. So instead of doing KEQ, we're going to be doing something called trial KEQ. Trial KEQ is a test to see if it is at equilibrium. Your textbook will call it trial KEQ. Sometimes the textbook will also call it just capital Q. But I personally think capital Q is weird. I usually call it trial KEQ because it's a trial, meaning like test, on the real KEQ. So we're going to be testing out the real KEQ. So trial KEQ equals the concentration of our products, PCl3 and Cl2, so in other words 0.6, and times another 0.6 over the concentration of our reactants, which is 2.5. So therefore trial KEQ equals, got my calculator here, 0.6 times 0.6 equals 0.36 divided by 2.5, and that equals 0.144. Okay, now as we can see, our trial KEQ is larger than our real KEQ. So our trial KEQ is bigger than our real KEQ. So in other words, what this is trying to say is that our trial KEQ needs to become a smaller number in order to reach KEQ. This needs to become smaller. So if you think of this thing right here as a fraction, because that's what it is, it's a fraction. This fraction needs to become smaller. Currently, this fraction is at 0.144. Now, in order for it to become 0.042, these numerators, or in other words, the products, need to become smaller, and the denominator, or this PCL5, needs to become bigger. That is how this fraction is going to become smaller, closer and closer to this. So if this PCL3 and CL2 need to decrease, and PCL5 needs to increase, that means it needs to shift to the left. That means PCL5 is going to be increasing. These things right here and here are going to be decreasing. So what is going to happen when trial KEQ is larger than KEQ? It's going to be shift left. So it shifts left. Okay? And if you have a hard time just like kind of memorizing that, you can just memorize this. If trial KEQ is larger than KEQ, hey, it's going to be shifting left. Okay? Again, I like to personally call it trial KEQ. Your book, for some reason, calls it Q. It is common to call it Q, but either one is fine with me. Okay, in your textbook, this is another question about shifting left and shifting right and stuff like that. And it's essentially the same kind of question. You can put the video on pause if you want and attempt it and see how you do. And so pause now to do it. Anyways, let's figure this one out. So maybe you did it, I don't know. Anyways, again, I'm going to write down my real KEQ. I like to write down all my information. So my real KEQ is 50. 50 is a big number. It's above the number 1. That means my products are going to be favored. And I'm given all these kinds of things. I love when the question says it reacts in a 1 liter container, makes the math extra easy. So if 3 moles of HI, that means 3 moles in a 1 liter container, that's 3 molarity. 3 moles of HI, 2 moles of H2, 1 liter container, that's just going to be 2 molarity. Okay, and 1.5 moles of I. Okay, 1 liter container, that's just going to be 1.5 molarity. Okay, so I'm going to look at my trial KEQ. Actually, first I'm going to write down my KEQ expression. KEQ expression equals HI, the concentration of HI. Since we have that 2 in front, we must square, okay, over the concentration of H2 and concentration of I2. Gas, gas, gas. I should be, yeah, that's fine. Anyways, so here's my KE. Oops, geez, what did I do here? I put the 2 on the outside. Right, there you go. And so anyways, here's my KEQ expression. Now, I know that KEQ, when it's at equilibrium, equals 50. So now we're going to do a test on it, or in other words, what we call is trial KEQ. Trial KEQ equals HI squared, so that is going to be 3 molar. 3 squared over 2, there's no squaring involved here. These are subscripts, they're not coefficients that go in front like this one. 2 times 1.5, 1.5, okay? So, anyways, trial Keq, you don't have to do this part, but trial Keq is going to be equal to 3 squared is just going to be 9 over 2 times 1.5 is just going to be 3. Trial Keq, you just do this all in your calculator if you want. 9 divided by 3 is just 3, like that. Okay, so trial Keq is less than 50, it is less than 50, but it is less than just regular old Keq. You know, 3 is less than 50, so I could have wrote that too. So what that means is that this trial or this test on Keq is that we came up with a number of 3. It wants to reach equilibrium. That means it wants to become the number 50. So how does this fraction right here become the number 50? Well, the numerator must become bigger. So that means products must increase. And these reactants must decrease. Once the products increase, the reactants decrease. It is a fraction, okay? And then that means it'll start to approach Keq. So how do we have, when those products increase, that means it needs to be shifting to the right. If it shifts to the right, the products will increase and the reactants will decrease. So, or if you struggle with this, you could just memorize if trial Keq is less than Keq, it is a shift right. You can memorize that. I personally don't memorize that. I memorize the ideas behind it. It's you get a better understanding of it. Anyways, so will a reaction occur? To answer the question, yeah, it does. Yeah. If so, which way does it shift? Shifts right. Okay. On a test, if you just wrote yeah, right, I'm not giving you marks for that. I want to see trial Keq and all that kind of stuff. So, anyways, I think that's obvious. Okay. Again, put this thing on pause. See how it goes, and yeah. And once you're back, you can answer this question. Anyways, Keq equals 50 again. We have the exact same reaction, but this time we have different concentrations of stuff. We have, I'm going to write my Keq expression equals concentration of Hi squared, because we have that 2 in front of there, over our reactants, the concentration of H2 divided by the concentration of I2. And now that's our Keq. I'm going to do a trial Keq. I'm going to test to see if we're at Keq. Yeah, anyways. So I see that my favorite, that 1 liter container, makes the math just a little bit easier. We have 5 moles of HI, so I'm going to go 5 moles of HI squared, because that's what this thing says to do. So 5 squared over, and I get this weird number, 0.7071, and I get another one too. H2 and I2 are both 0.7071. Okay, and so trial KQ equals 25 over 0.7071 squared, technically, because they're the exact same number. Trial KQ equals, I got my calculator because I can't do that in my head, 25 divided by 0.7071 squared equals, and the number I get is 50. So that means trial KQ is equal to KQ. Okay? So when you have a scenario like this, when trial KQ is at KQ, that means you trial KQ, again, you tested it to see if it's at equilibrium, and what we got is, yeah, it is at equilibrium. Okay? So will the reaction occur? Nope. Okay? If so, which is it? Like, it's not. So it's not trial KEQ is equal to KEQ. And so therefore, if you don't know, this is the symbol for therefore. Therefore, the reaction is at equilibrium. Again, if you're answering this question on a quiz or a test or something, I want to see the math. I want to see you do trial KEQ. So yeah. Anyways, that's that. This one right here. Now, this one is similar, but more difficult. You can try doing this one yourself, or and putting on pause. But I'm going to answer it right now, anyways. So this one says KEQ, and exactly 1 mole of everything is placed in a 100-liter vessel. I hate the 100-liter vessel. I like the 1-liter vessel. Anyways, and the mixture was allowed to react. Find the equilibrium concentration of each gas. Okay, so first off, I got to do that annoying little math of 1 divided by 100, and to find the concentrations of everything. Okay, so 1 divided by 100 is just it's supposed to be 3 sig figs. So like this. That would be their concentration of everything in our reaction vessel. Okay, so that's the initial concentration. I'm going to go quickly do a trial KEQ. First, I guess I should do a KEQ expression. I'm going to do it right here. Our KEQ expression equals CO2 H2, so our products over our reactants, concentration of CO times H2O. I'm going to do a trial, so I'm going to write trial right here. Trial KEQ equals 0.01 times 0.01 over 0.01 times 0.01. Okay, and I'm not sure how good you are with math. I'm sure some people are using their calculators right now, but you should kind of realize that's 1. Okay. Now, so what we see here is trial KEQ is larger than KEQ. So what that means is that since trial KEQ is larger than real KEQ, because KEQ is this number right here, equals 0.4. that means there's too many products and we need to shift towards this way right here. Okay, so this was really important information, shifting to the left. Okay, so I want to remember this really important information. So important, I'm going to put a little star over it. Okay, now I need to go, I'm going to make my ice table. So I'm going to write my whole equation again, CO plus H2O, CO2 plus H2. I'm going to choose a different color. We're going to go purple for ice. And go back to red. Actually, you know what? I'm going to go blue. I'm going to fill in my ice table. These are our initial concentrations. We're not at equilibrium, so they're initial concentrations. So I'm going to write that for every single number. 0.01, and I should be writing 0, afterwards. But I was going to remember there are 3 sig figs. 0.01, 0.01, 0.01. Okay. Now, this is the key part, and this is why we starred this thing right here, and why it was important to figure out, is it shifting left or right? So it's shifting left. So if it's shifting left, that means since it's at a 1-to-1 to 1-to-1 ratio, these are all going to increase by a factor of x. If the reactant side is increasing by a factor of x, the product side is going to be decreasing by the factor of x. And then 0.01 plus x equals 0.01 plus x. And that's the same thing for this one. 0.01 plus x. That means this is 0.01 minus x and 0.01 minus x. Okay. I'm going to plug these into my KEQ expression. So I'm going to go KEQ, and I already have my KEQ expression here. I don't feel like rewriting it out, so I'm just going to start plugging in all the numbers. So I'm going to plug in real KEQ number, 0.0, oh, sorry, it's not 0.04, it's just 0.4, okay, 0, equals our products, which is 0.01 minus x squared, because there's 2 of them, right? It's going to be 0.01 minus x times 0.01 minus x. So I could just write 0.01 minus x. Since there's 2 of them, I'm just going to write it squared. Since there's 2 of these on the reactant side, I'm just going to write 0.01 plus x squared as well. Okay, I'm going to choose green. I don't know why I'm getting funky with the colors, but bad color green. I'm going to take the root of both sides, okay, and we'll go back to blue, equals, the roots take out the squares, so this is going to be 0.01 minus x over 0.01 plus x, and 0.4, root 0.4 equals 0.6324. 6324. Okay. Okay. Now for the fun math part, I need to isolate my x, so I'm going to times both sides by 0.01 plus x. I'm going to write this in red, I guess. I'm going to just go times 0.01 plus x. Okay, and this side, I don't know how to write it. I'm kind of running out of room here. Times by, same thing, 0.01 plus x. Okay, and this will cancel out with this whole side. I gotta do some math on this one. So if we can remember our FOIL or all that kind of stuff from math 9 and 10 or something, but we times these like that. First one, I'm going to go 0.6324 times 0.01. So times 0.01. And so you can just move the decimal place over a couple of times right there. So it'll be 0.12. So one. Oops. And then plus, and then the 0.6324 times this x is just going to be 0.6324 x. Okay, and then we have this equaling 0.01 minus x. Okay. Okay. Now, what I'm going to do is I'm going to isolate my x's and all that kind of stuff, and I'm going to go back to, well, I'll stick with red. I'll stick with red. So in order to get rid of this minus x here, I'm going to plus x here. And if I do that to one side, I might plus x on this side. And then I'm going to take all this information, and I apologize, but I'm going to move it all the way up there. 0.6324x plus x is going to be just 1.6324x. This is a 1x, so I'm plussing an x on both sides. And plussing this x on both sides. Anyways, so then what I'm going to do right here is I'm going to subtract, so we'll minus 0.00632 from both sides. So I'm going to minus it from this side as well. Okay, minus 0.632 from that side as well. So I'm going to use my calculator to do that. 0.01 minus 0.00632 equals, and I get this number equaling 3.676 times 10 to the minus 3. Okay. And then what I'm going to do is I'm going to divide by 1.6 on both sides, divide by 1.6324 on this side, divide by 1.6324 on that side. Shift to purple, cancels out, and so therefore I get x equals whatever that number is, 3.676 divided by 1.6324 equals, and I get x equals 2.25 times 10 to the minus 3. Yay, we're done, but we're not done because we need to plug it back into our regular original equation. So the concentration of H2 equals 0.01 minus x. So 0.01, so 0.01 minus 2.25 times 10 to the minus 3 equals since this is the exact same thing, it's just going to be CO2 is going to equal the exact same number. And CO is going to be 0.01 plus 2.25 times 10 to the minus 3. And since H2O is the exact same thing, this is going to be H2O. Concentration is also 0.01225. And I should be writing molarity after everything. Yay! You're done. That's that. Please like and subscribe.